Welcome everybody, this is week number 6 in the Parallel Programming Concept course in OpenHPI. In this week we want to finalize the course with a discussion of several advanced topics and general topics in the area of parallel programming. Specifically we want to go into the idea of design patterns and methodologies that allow you to tackle a particular parallelization problem. So while the last weeks basically covered tools, programming paradigms and other algorithmic structures that you may use in order to implement a parallel piece of software, we now want to answer the question, what are generalized strategies to deal with the problem at all? If you remember what we talked about in the last week, in week number 5, then this was basically about shared nothing systems or distributed memory systems as they are sometimes called. And shared nothing systems have some unique characteristics. The main relevant point is that the interaction of parallel tasks in a shared nothing system relies on messaging. And this reflects in the programming models such as MPI, but also in the general way of how we structure the software in order to get speed up by parallelization or maybe scale up in order to compute a larger problem. We talked about some high-level abstractions like channels and actors, and you were hopefully able to see that when you use these high-level abstractions, it becomes easier to develop a scalable software for a shared nothing environment so that at the end your overall development time reduces. And given that background, we now covered shared memory and shared nothing systems and can now move one level higher and try to understand how do we approach the problem of parallelization in general. And you may remember this image, we showed it several times. The idea is that when we want to understand the parallel programming problem, it is basically a match of a parallel application we somehow design with some kind of rules to a particular execution environment. So we have design spaces and design possibilities in the coding of the application, in the architecturing of the application, and we have also design choices and alternatives on the execution environment side. For example, when we talk about the particular configuration, the kind of interconnect we're using. So we have flexibilities on all sides and we need to match our results at the end so that they fit to each other and that we still get a benefit from our parallelization attempt. And when we now want to take the concept of design patterns and try to understand what parallel programming has, what kind of relation parallel programming has to design patterns, then the first thing you need to consider is that parallel programming basically is a question of experience. This is something you may read in a book or as here you listen to a lecture in a course, but at the end the only real way to deal with good and feasible parallelization is to have experience, to do it by yourself or to have people, developers that are really able to find concurrency and exploit it in one or the other way. So the rule of thumb in parallelization and maybe in programming at all is that somebody else may be smarter than you. So it is always a good idea to reuse existing ideas, existing concepts and structures from other people. They made their own experiences and they maybe were able to summarize them in some kind of template or rule that helps you in developing your own software. And this kind of thinking is actually the foundation for the idea of design patterns. So a design pattern in software is a best practice, and this best practice is somehow formulated in a way that you have a question that tells you, is this applicable to my problem? And then you have an according solution proposal given by the pattern itself. And this kind of idea, having template solutions, is not new. This is something that is well known for decades in computer science, especially with the book by Gamma and others about design patterns in object-oriented programming, also called the Gang of Four book. And this is our example for what we now want to apply to parallel programming. So we want to take the idea of software design pattern and want to apply it on the parallel programming world. Is this possible? Yes, it's possible. There are a couple of proposals and ideas we will show you. When you look into the literature, you see that there are two groups of things that are called parallel programming patterns. One group are structured parallelization methodologies where people recommend you to do a parallelization in this or that way, take first this step, then this step. And the other group of ideas regarding parallel programming patterns are building blocks, algorithmic building blocks, templates for how to structure your software in order to solve a particular parallelization issue. So let's have a look into both of these classes. The first thing I want to show you is an excerpt from a famous book which is called Patterns for Parallel Programming by Timothy Madsen and others. And this book contains a broad collection of interesting parallelization patterns. And in order to categorize them and bring them into context, the book proposes 4 design spaces. A design space is a phase in the development of your parallel programming or parallel program where you have choices, where you have design opportunities, design choices in order to say, I solve this problem either in this or that way. The book defines 4 design phases. The first one is the finding concurrency phase. This is the part where you take your original computational problem and start to find concurrent activities. So you try to answer the question, where is exploitable concurrency in this particular problem? This investigation may rely on an existing serial version of the program, or it may simply rely on a description of the overall computational problem. The second design space is the algorithm structure design space, where you have an idea of the existing concurrency in your problem, and then you start to develop an algorithm that actually solves your computational problem. And the structuring of this algorithm, how to design it, how to put tasks into context, this is what happens in this phase, and there are also proposals for design patterns in this particular area. The third phase is the supporting structures phase, where you have an algorithm, you have a structure, you have an idea of what is going on concurrently in your solution, but now you need additional stuff in order to come to a real implementation. For example, you need shared data structures. And there are some ideas in the book how to deal with that part of the parallel programming question. And the last design space is the implementation mechanism design space. This is rather obvious. This is the point where you choose programming languages, libraries such as OpenMP in order to solve your idea of a parallel algorithm. So let's have a short look into the different phases in order to give you a better understanding of what that means. The finding concurrency design space, the first design space in the development of a parallel solution, has the idea, as I said, to find exploitable concurrency. One example is the data decomposition pattern. So with the data decomposition pattern, we have a particular context. This is the kind of problem domain where this pattern matches, where we may want to use it. In the example of data decomposition, this is basically the fact when we have a problem where computation is organized around large data sets, like for example, weather simulation or any kind of big data analysis. This is something where a data decomposition sounds natural, especially when we have the case that similar or maybe even the same operations are executed on different parts of the data. And when we have such a situation, when this is our context, our problem context, then the pattern description says a good solution is now to organize some kind of array-based data access in rows or in blocks or maybe in multiple dimensions. When we have recursive operations on this big data, then it may be good to have recursive data structures too. And so there are some recommendations how to deal with that. The other example in this design space is the group task pattern, which explains the situation where the grouping of tasks actually makes sense. So you identified your concurrency, and now it may be good to combine some of these tasks in order to make them one big task in the overall algorithm development. One example is when you have embarrassingly parallel problems, where you have a lot of independent tasks that have no data dependency on each other. In this case, it makes sense to take all the embarrassingly parallel tasks and put them into one group so that they can handle it as one thing in the implementation. The second design space is the algorithm structure design space, where we try to design our algorithmic flow. And here the interesting question is, what is your guide in the control flow of the parallel algorithm? And Madsen proposes 3 choices. You either can organize the algorithm by the tasks that you found, by the concurrent activities you identified, or you can organize your algorithm according to data dependencies between their tasks, if this is more natural for the design of the algorithm, or you can organize it by the processing of data all through the overall application. And you see on the slide that there are different design patterns that can be derived from the choice of a particular algorithm organization. For example, if you think that your concurrent activities are a good guide in order to structure your parallel algorithm, then this naturally sounds like task parallelism. Or if you have the same thing but in a recursive processing fashion, then divide and conquer may be a good idea. And so you have different ways of creating an overall structuring, and based on this choice, the book proposes several design patterns to you. Let's look into an example to get a better feeling for what that means. We take as an example here bubble sort, which is hopefully known to you. Bubble sort is a sorting algorithm which in the serial version works in that way that you have, for example here, a number of numerical values, and you go through the list of numerical values, you do a pairwise comparison, and whenever you see that a pair of numbers is not in the right order, then you switch them, and then you continue, and you do this in a loop so often until you reach the point where you make no more swappings, and in this case, your overall line of numbers is sorted. This is bubble sort. This is a well-known algorithm. And there's a serial version expressed here in the picture. And when we now have the task of designing a parallel algorithm for it, the question is, how do we apply this design space idea? And as we heard, the first step is finding concurrency. So you need to find inherent concurrency in this problem. And if we look deeper into the bubble sort example, we see that we basically have the same kind of operation being done on different parts of the data. This is one aspect that is relevant here in the serial algorithm. The second relevant aspect is that we have multiple rounds. So the same thing is done several times. And the third thing you hopefully identify is that there is some kind of data dependency. So the serial version relies on the fact that the second comparison comes after the first comparison because they both share one number. And this one number may be changed after the first step. So this is a kind of a data dependency that is hidden in here. And therefore, one good idea would be to somehow take the round aspect of bubble sort and take this as concurrent activity and try to formulate a parallel solution that relies on this particular aspect in order to get a parallel version. And the proposal here, one example proposal for getting a parallel version would be odd-even sort. And with odd-even sort, we apply the task parallelism idea. So we say, let's take different compare activities and let us parallelize them, but in a way that we do not have these data dependencies that may hinder us from getting a true and good scalable parallelization. So odd-even sort is doing this by taking multiple comparisons at the same time. So this is the point where you have concurrent activities that you may parallelize on a particular piece of hardware. And you do these comparisons, as you can see in the example, in a way that that both operations operate on completely different sets of the input data. So you first compare all the even numbers with their neighbors and then all the odd numbers with their neighbors. And you do this until you have a final result. And as you can see in the example here, we get a faster execution. We have less steps, less timestamps steps. We have still a high number of comparisons, but we can parallelize them. So the overall result of getting a speed up in our algorithm is achieved by parallelizing the different compare tasks we have in the serial version. So these are the two design spaces, the first two design spaces. The third one is now to get closer to the implementation. So we would take for example, our odd-even sort and would now start to write down code, to write down programs, maybe pseudocode still in order to not bind ourselves too much on a particular technology, but we already think about shared memory or shared nothing. We define global variables or global data structures. And the third design space in the medicine book says that there are different ways of doing a program structuring according to the execution environment, but also according to the chosen concurrency level. So you see examples on the slide such as single program, multiple data, master worker, fork join, and several other ideas we already discussed in the course. The program structure is one thing here. The second thing is the data structuring. So you may also think in this part about the kind of shared data you have. Is it shared data that is only read by the participants? Is there a reader-writer scenario where one task is writing data, but multiple others are reading it? Do we have independent subsets of the data where processing happens at the same time? So these kind of thoughts should be done in this design space here, where you have an idea of your concurrent activities, and maybe you identify that your chosen algorithm structure is badly designed or can't really work in a real parallel environment. Then you may need to backtrack to earlier steps in order to reevaluate your decisions. And the last step then is the implementation mechanism. We don't want to talk about this here because we had this in the earlier weeks. And here you see a summary of all the different patterns that are described in the medicine book. So you have the different design spaces and the according approaches that help you in structuring your parallel programming in a better way. So the medicine book was quite successful. It was a huge thing. It's still very valid and a good read. But then it turned out that you can extend this idea. And the authors of the books and several other colleagues, especially from Berkeley University, did that and created the Our Pattern Language repository, OPL. You see the web link on the slide. And OPL simply takes the medicine ideas and expands them and gives you more patterns and more categories. So you see here in the structuring that they distinguish between the patterns for concurrent execution in itself. You see well-known terms such as SIMD, MIMD, message passing in here. Then we have the implementation strategy, where you also see a lot of things that you should know meanwhile, such as SPMD or the fork join model. Then we have an algorithm strategy, which somehow is linked to the implementation strategy. So for example, task or data parallelism. And then on the high level, we can talk about high level structuring of either data or computation, or maybe example patterns for particular kinds of computations. So this is OPL. And here's an alternative description of what the different classes means. So when you think about software in terms of structure diagrams, architecture diagrams, boxes and arrows, things have relations to each other, then this is structural patterns. Yeah, this is the question of how to structure your software and your different modules and classes or functions, whatever you have. Computational patterns then relate to the fact what happens in the boxes. So what is this particular component, this particular library function doing when we actually execute it, and how does that relate to parallelization? And so we also have the different other pattern classes. The web page of OPL, which is publicly available in public, contains a lot of different documentations. It's a wiki page, so things are added over time. And you can see this as the condensed experience of many people that have real-world experience or real-world problems with parallelization. So that's a very good reading source in order to bring you closer to parallel programming design patterns in practice. When we take an example, one example would be the discrete event pattern you can find on the page. So when we open this PDF, then we see that the pattern has a name and it has a problem statement. In this particular part, the problem is an irregular task parallel problem, which is similar to the design space ideas we saw in the medicine book. We have some implicit ordering constraints in our tasks, so they have no regular structure, but they have some kind of ordering in between them. You can't really draw that down as, for example, a structured grid, but it's highly irregular, so it's a wild graph, and this is your parallelism, your task parallelism, and the pattern now tries to answer the question, how do you deal with that in your implementation? And the answer here in the OPL for the discrete event pattern is that you use a data flow-based approach where you define the notion of events. So the relationship between tasks in your parallel application is expressed by events being sent or consumed. This may remind you of the actor model, but the actor model is actually an implementation strategy to, for example, in order to realize such a discrete event pattern algorithm. You take this pattern, you design your algorithm accordingly, and then in the next step you would take a particular implementation strategy to do that. So you find a lot of these patterns in the OPL. It has a wide uptake meanwhile, so you can find different links and people contributing to it. So if you're interested in design patterns for parallel programming, this is a very good source. Another source which recently came out is the book by Kuhl et al., Structured Parallel Programming. And as you can see here in the summary list, a lot of things repeat. Yeah? So a lot of things you can see in the parallel design patterns collections are also stated here. You also have some relation to serial programming and the according patterns. So all in all, our investigation or our view on the parallel design patterns is that there are well accepted ways of dealing with parallelism. They are described, for example, in the OPL. And if you want to rely on that knowledge, just consult it, just read it, and try to figure out if the particular design patterns match to your parallelization problem or not.